This lesson, we're going to learn how to use factor theorem more efficiently by finding all the possible values for the factors of a polynomial instead of randomly substituting different x values into a polynomial to find a factor. In order to understand the extension of the factor theorem, which is also known as the rational root theorem, we will expand the following polynomial from the factor form to the expanded form to investigate the relationship between these two forms. Let's expand this polynomial in factor form. So we use distribution property to expand the first two brackets, and then we collect the like terms in the first bracket, and then we use distribution property again to expand those two brackets. Then we collect the like terms. Now we have the expanded form. Now let's take a look at the first term of the expanded form. 2x cubed. 2x cubed was coming from 2x cubed here, which was coming from x squared times by 2x, which was coming from x squared times by 2x, and which was coming from x times by 2x. So we know the first term of the expanded form is always the product of the first term of the factors. Next, let's look at the last term of the expanded form, negative 30. And this negative 30 was coming from this negative 30. And this negative 30 was coming from positive 6 times by negative 5, which was coming from this positive 6 times by this negative 5, which was coming from negative 3 times by negative 2 times by positive 5. So therefore, we know the last term of the expanded form is always the product of the last term of the factors. So we know all the possible values of the factors will be in the form P over Q, where P is all the factors of the last term of the expanded form, and Q is all the factors of the first term of the expanded form. So now let's do some examples to see how we can use the values of P and Q to factor a polynomial. Example 1. In order to factor this cubic function, let's first define our value of P and value of Q. P is the last term of the expanded form, and Q is the coefficient of the first term. So we say factors of P will be factors of negative 7, which is positive negative 1 and positive negative 7. And factors of Q will be positive negative 1 and positive negative 3. Then we can find all the possible values of P over Q, which is positive negative 1 over 1, positive negative 7 over 1, positive negative 1 over 3, and positive negative 7 over 3. Since the top two numbers are integers, so we will simplify them to positive negative 1 and positive negative 7. Instead of randomly trying different x values into the function f(x) to get a 0, now we know those are the only a numbers that we have to try. If none of the numbers can give us a 0 as a remainder, then we can say the function f(x) is not factorable. Let's try those possible values one by one to see which one can give us a 0. So fi1 is a 4, fi-1 is negative 56, fi7, which is 280, fi-negative 7, that's not 0. fi1 over 3 is a 0. Now we stopped. However, now we have to write it as a factor. So how do we write this as a factor? We know x equals 1 over 3, multiply by 3 on both sides, subtract 1 on both sides. Now we get 3x minus 1 equals 0. So we know our factor is 3x minus 1. Remember, when you write as a factor, we do not use any fraction. Once we find a factor, then we use syntactic division to divide it. First, let's draw a division symbol. Next, fill in the coefficients of the dividend. Then we have to find our value of the divisor. Remember, our divisor is actually 3 times x minus 1 over 3. So the divisor will be positive 1 over 3. Let's do the division. Bring the 3 down. 3 times by 1 over 3 becomes 1. Negative 19 plus 1, negative 18. Negative 18 times by 1 over 3, negative 6. 27 plus negative 6, 21. 21 times by 1 over 3 becomes 7. So now we have a remainder of 0. And remember, your quotient has to be divided by the coefficient of the divisor, which is a 3. So we have to divide it by 3 here. So our real quotient will be 1x squared, negative 6x, and 7. Now we can rewrite fx as divisor 3x minus 1 times by the quotient x squared minus 6x plus 7. Now we have a quadratic trinomial. In order for us to find out whether or not this quadratic can be factored down further, let's use discriminant to check b squared minus 4ac. As we calculated, the number is actually a 8. 8 is not a perfect square. That means this quadratic trinomial cannot be factored down further. Therefore, the factor form for fx will be 3x minus 1 times by x squared minus 6x plus 7. Example 2, once again, let p represents the constant and that q represents the coefficient of the first term. Then we're going to find the factors of p and factors of q, and then we're going to define all the possible values of p over q. Before we substitute all those values into the fx, let's remove the ones that are repeating, such as 2 over 2, 10 over 2, 2 over 6, and 10 over 6. After that, we substitute the remaining into the function fx to see which one can give us a 0. So as you can see, I tried many different numbers until f at 5 over 3, which is going to be a 0 now. So I know x equals to 5 over 3, multiply by 3 on both sides, and remove the 5 on both sides. Now I know 3x minus 5 is a factor. Once we have a factor, then we use syntactic division to divide it. As you can see, the remainder is 0. Remember to divide the quotient by the leading coefficient of the divisor, which is a 3. Now we can rewrite fx as the divisor 3x minus 5 times by the quotient 2x squared plus 3x plus 2. Once again, we have to verify whether or not this trinomial can be factored, so we use the discriminant. Once we find the value of the discriminant, which is a negative 7, that's not a perfect square, so we know it is not factorable. Therefore, we know the factor form for fx will be 3x minus 5 times by 2x squared plus 3x plus 2. Example 3. As you can see from the given function, the function fx has a degree of 4, which means sometimes we might need to use factor theorem more than once in order to factor a polynomial. So let's try to factor them. First, we define our p and q, and then we find the factors of p and factors of q, and we find all the possible values of p over q and remove all the ones that are repeating. Then we substitute all those values into the function fx to see which one can result in a 0. As you can see, f at 5 over 2 becomes 0. That means x equals to 5 over 2. Multiply by 2 to remove the fractions and subtract 5 on both sides. Then we can see 2x minus 5 is a factor. Once we find the factor, then we use syntactic division to divide it. Remember to divide your quotient by the leading coefficient of the divisor, which is a 2. Then we can rewrite fx as a divisor times by the quotient. Now, let's define our quotient gx, and we're going to find a different p values and q values. So that's fine. Factors of p will become positive negative 1 and positive negative 2. And the factors of q will become positive negative 1 and positive negative 3. So instead of writing all the possible values again, we can use the original one and we just cross out the ones that we don't need. Since there's no p values of 5 and 10, so we cross out those two columns. And since there's no q values of 2 and 6, then we're going to remove those two rows. And now we're going to try those a values for the new function to see which one works. However, Because originally for the f function, positive -1 and positive -2, it doesn't work. That means for the new function, gx, the positive -1 and positive -2 will not work either. Now we substitute the remaining 4 numbers into the function g to see which one can give us a 0. So we keep on trying until g of -2/3, which is a 0, so we know 3x plus 2 is a factor. Once we find a factor, we use syntactic division again to divide it. Remember to divide the quotient by 3, as 3 is the leading coefficient of the divisor. Then we get gx as divisor 3x plus 2 times by the quotient, x squared minus x plus 1. Once again, we need to check whether or not this trinomial is factorable. So we use the discriminant to check. Discriminant turns out to be a -3, which is not a perfect square. Therefore, we know this cannot be factored down further. Therefore, we say fx equals to 2x minus 5 times by 3x plus 2 times by x squared minus x plus 1. And this is our factor form for fx. The next part of the lesson, we're going to learn how to determine a polynomial equation given the roots. There are some key ideas that we have to know. First, a polynomial function with n degree has n complex roots. For example, if a degree of the polynomial function is 5, then you will have 5 complex roots. The maximum number of x-intercepts always equal to the degree of the polynomial function. For example, if the degree of the polynomial is 5, then you will have maximum of 5 x-intercepts. Minimum number of x-intercepts, it really depends on the degree of the function. If the degree of the function is 1, then you will have minimum of 1 x-intercept. If the degree of the polynomial is even, then you will have 0 x-intercept as a minimum number. Imaginary roots always occur in conjugate pairs. In general, if a plus bi is one root, then a minus bi will be another. Example 4. Find the family of cubic functions whose x-intercepts are 2, -3, and half. So we know the x-intercepts. We have to go back to find the factors. That means we have to remove the 2 and -3 and half on the right-hand side of the equation. We need to have a 0. So after we do the calculation, we can see x minus 2 is a factor, x plus 3 is a factor, 2x minus 1 is a factor. Therefore, we can say our family function fx equals to x minus 2 times by x plus 3 times by 2x minus 1, and with a as a leading coefficient in the front. Part B, we want to find a particular member of the family that passes through the point 4 and -196. This means we want to find the unknown variable a. So we're going to substitute the point in to the function fx to find the value of a. So y value will be -196, x value will be 4. After we expand and simplify and solve for a, we get a equals -2. Therefore, the particular member that's called gx equals to -2 times by x minus 2 times by x plus 3 times by 2x minus 1. Example 5. We want to find a family of cubic functions. However, this time we only have 2 x-intercepts. So we know those 2 x-intercepts, let's convert them back into the factors. So we know there are 2 factors, x minus 2 and x plus 3. Now let's use the factors that we find to generate the family of cubic functions. So the first function I write it down is fx equals to a times by x minus 2 times by x plus 3. But as you can see, the degree of this function right now is only 2. But I need to have a cubic function. That means I need to have degree 3. So I'm going to add exponent 2 on the first factor. Or I can do the family function called gx will be b times by x minus 2 times by x plus 3, and I can add the exponent on the second factor. As you can see, now we have generated 2 different possible family of cubic functions whose x-intercepts are 2 and -3. Part B, we are going to find particular member of the above families whose graph passes through the point 1, 4. Once again, we substitute the point into the function fx to find the value of a. Once we substitute 4 into the y, 1 into the x, simplified it, and solve for a equals to 1. Therefore, we say the function hx equals to x minus 2 squared times by x plus 3. Let's repeat the process for the family function gx. Let's substitute the point 1, 4 into the function gx to find the value of b. Then we substitute 4 into the y, 1 into the x, simplified it, and we solve for b. b is negative 1 over 4. So let's call this particular member kx equals to negative 1 over 4 times by x minus 2 times by x plus 3 whole thing squared. Example 6, we want to write a polynomial equation with the roots 2 plus minus root 3i. First, let's find the factors from the given roots. So we know the roots. Let's move every single term to the left of the equal sign to find the factors. Then we can say the family function fx equals to a times by x minus 2 minus root 3i times by another factor x minus 2 plus root 3i. Since the question only asks to write a polynomial equation, that means we're going to let a equals to 1 to find one possible polynomial function. After we substitute 1 into the function fx, we're supposed to expand and simplify. But if we look at it closely, we can see they have common term x minus 2. And if we replace x minus 2 with the variable a, then I can read like this. A minus b times by a plus b, which is the factor form of difference of squares. That means the expanded form will be a squared minus b squared. Now the expansion will become a lot easier. This is a perfect square, and root 3i whole thing squared will become 3i squared. And we know I squared is negative 1. That substitute negative 1 into the I squared, collect the like terms, and simplify. We will get x squared minus 4x plus 7 as our polynomial equation.